In traditional software engineering, continuous integration pipelines provide a reliable baseline. You write a function, run a test, and if the output matches the expected result, you get a clean green checkmark. But the moment you integrate a large language model, that predictability breaks. Traditional code relies on determinism, the guarantee that a specific input will yield the exact same output every single time it executes. Large language models break this assumption because they function as probabilistic engines. Send the exact same prompt to a model twice, and it often returns two different responses. The architecture is designed to sample from a distribution of probable tokens, introducing inherent variance into the system. This visualizes the two architectures. On the left, standard deterministic logic. Input A maps directly to output B. On the right, the LLM paradigm. Input branches into a probability matrix, yielding multiple outputs. Because of this, a single unit test is statistically meaningless. Without a framework to handle this variance, developers often fall back on vibe-based testing. A user reports a hallucination, an engineer tweaks the prompt, runs it once or twice, sees a better answer, and assumes the problem is solved. But because the model samples from a probability distribution, a passing test is merely a single data point. It is not a verdict of system stability. You haven't proven the prompt is more reliable. You may have just sampled a lucky token sequence. This reliance on isolated testing leads to silent regressions. You change a prompt to handle one specific edge case, and it works. But without rigorous coverage, that same change can secretly degrade the model's performance on dozens of other standard operations in production. The instinct is to treat this as a coding error, searching for a logical flaw in the prompt syntax. But LLM failure is a measurement problem. Manual debugging must be replaced with a systematic, automated discipline called evaluation, or eval. Building this system requires addressing fuzzy correctness. Unlike a regex pattern strictly matching a string, there is rarely a single binary correct answer. If you ask a model to summarize a support ticket empathetically, correctness spans a range of acceptable subjective responses. You cannot measure what you have not defined. Engineers must map out the exact dimensions of correctness before they can evaluate any output programmatically. To evaluate an LLM, the system requires a rigid baseline to compare outputs against. This starts with the first core primitive, the Golden Set. A Golden Set is a curated collection of high-quality expected input-output pairs. It must be built using real, anonymized production queries. Testing against developer-imagined happy paths creates a false sense of confidence, as users often phrase things in ways engineers don't anticipate. Once you have the inputs, you need the second primitive, the rubric. This operationalizes subjective criteria, like helpfulness or tone, into concrete, scorable vectors. This chart shows how a rubric structures that data. Along the x-axis, we have specific quality dimensions: relevance, coherence, and factual accuracy. As the raw text chunks on the y-axis are processed, they map directly to numeric scores across these dimensions. A golden set without a rubric is just a collection of unformatted data. Together, they form the ground truth of the system. Even with a rubric, we must account for generation variance. The parameter controlling this is temperature. High temperature settings cause the model to sample from a wider probability space, creating more varied and unpredictable responses. This graph shows what happens. If we run one test, we get a single score. But when we actually run the same prompt 100 times, we see a wide variance cloud.
The initial test was just statistical noise. To isolate the performance of the prompt from the randomness of the model, temperature must be locked to 0 during offline evaluation to enforce determinism. Without running high-volume sample sets and calculating the variance, you cannot determine if a score change represents a real improvement or a random fluctuation in the model's output. While human review is the gold standard for fidelity, it cannot scale for every continuous integration run. We need automated alternatives. This chart maps the scoring continuum. At the bottom right, optimizing for speed, we have heuristics. Moving up, we introduce semantic similarity evaluation, using embeddings to measure closeness in meaning to a reference. But semantic similarity can falsely pass incorrect responses, sharing similar vocabulary. For high nuance at scale, we use LLM-as-Judge to score outputs against the rubric. LLM judges typically use point-wise evaluation, scoring a single output from 1 to 5, or pairwise evaluation, which A/B tests two outputs to find a winner. Because models have their own biases, judges must undergo periodic calibration.
You take a sample set, score it with humans and the LLM-Judge, and measure their agreement to ensure reliability. No single method is sufficient on its own. Relying purely on one invites either significant compute costs or semantic blindness. Evaluation is even more complex in retrieval augmented generation, or RAG, where the model fetches external data before answering. When a RAG system hallucinates, you must isolate the failure. Was it retrieval, augmentation, or generation? The RAG triad is the observability framework for this. First, context precision. Did the database fetch correct information? Second, faithfulness. Did the model use that data? Third, answer relevance. Did the response actually address the user's intent? The RAG triad provides engineers with the precise coordinates of data corruption, allowing for targeted fixes rather than blind prompt adjustments. Comprehensive evaluation requires two environments: offline testing before deployment and online monitoring in production. This requires balancing economic trade-offs. Offline evaluation uses expensive, capable models to catch regressions, while online monitoring uses cheaper, faster models to handle live traffic. These assemble into the 5-layer eval stack. At the base is Layer 1, heuristics, catching structural bugs on every request. Layer 2 uses semantic similarity to catch meaning-level failures. Layer 3 uses a heavy offline LLM-Judge as a deployment gate, followed by Layer 4, a lightweight online judge. Finally, Layer 5 adds periodic human spot checks to calibrate automated judges. This layered approach provides the statistical signal needed to iterate on prompts with the same version control discipline used in traditional software development. Attempting to build a 5-layer stack from scratch creates significant architectural overhead. Most teams should start with a minimum viable product, a system that provides the baseline security needed to ship a feature. Step 1. Curate 50 real queries for your initial golden set. Step 2. Add one heuristic check, like a required JSON field. Step 3. Add one LLM-Judge, targeting your most critical rubric dimension. Because we are operating in an architecture driven by probability, structural predictability must be engineered from the outside in. The non-deterministic nature of these systems requires us to shift our focus from prompt syntax to the automated rigor of the evaluation pipeline itself. In the era of probabilistic software, this is the only way to build systems that can actually be trusted.